Alright, so I want to give you an intuitive explanation of electric fields. So before we get into electric field though, let's revisit a very familiar concept of gravitational fields. So let's say we have two masses, right? So let's call this mass m1. Let's call this smaller mass m2, okay? And once I place them near one another, let's say a distance r is between them, then what will happen, Newton tells me, is that any two masses in space will always attract one another. So space you can think of in outer space, or a general three-dimensional coordinate is also in space. So that's up to you. But regardless of what you call space, m1 will be always attracted towards m2, and m2 will always be attracted towards m1. So let's call this F21, meaning the force that m2 exerts on m1, and let's call that F12, the force that m1 exerts on m2. And by definition of Newton's third law, these two forces must exactly be equal regardless of the two masses. Their magnitudes must exactly be equal, and they must be directed oppositely as they are. Mathematically, Newton's gravity, we call that Newton's law of gravitation, is written as follows. Newton's gravity, let's call that for short. Newton's gravity is defined as follows. So the force of gravity is equal to Newton's gravitational constant times m1 times m2 divided by the distance squared between the two masses. So the force of gravity is proportional to the product of the masses. That means if you increase or double the mass of m1 and keep m2 constant, then and keep everything the same, then basically the force of gravity will be doubled. And it is inversely proportional to 1 over r squared. That means the force will go down by 4 times or 4 factors if you double the separation distance. All right. So that is what Newton's law of gravity tells me. And there's a bigger question though. How does m2 know that m1 is there? How does m2 know that if I place m2 exactly where it is, that it will be attracted towards m1? How does it know to be attracted? Is there some rope or something that pulls m2 closer to m1? Well, what I can tell you is there's this idea of how we can visualize these things. So we can visualize m1 having this imaginary space around it with some information. So let's say this is m1, and everywhere around m1 there is this entity, there is this kind of field around m1 which tells everything else that here, exactly here in space, m1 is there. This is where m1 lives, and we call this entity here the field of m1, field or gravitational field of m1. Okay, so let's say now I bring in m2. M2 was not originally near m1, so I force m2 to be closer to m1. I bring it in from very far away, let's say from infinity. I bring in m2. I had this m2 with me from at infinity. I bring it in and I place it in the vicinity or in the neighborhood of m1. Then m2, due to this field of m1, knows that m1 is nearby, and m1, because it's another mass, m2 is one mass by itself, they will move as close to each other as possible. They will always attract one another as per Newton. Okay, so this is the idea of gravitational field. Can we give it a mathematical formulation as often is needed in physics? Well, let's try. So let's define this as the gravitational field, and we want to write down an expression for gravitational field. Well, gravitational field is basically the entity around m1 that tells every other mass that you bring nearby that m1 is there, right? So therefore, m1 being a mass itself, it exerts a force, right? So m1 will exert a force of gravity. So let's write that down. and m1 will exert a force on of gravity on any other mass. Let's call that mass m2. Any other mass, m2, right? So whatever mass I bring in will experience this field around m1. So that depends. Do I have m2 with me? Do I have 2 times m2 with me? Do I have 3 times m2 with me? So the force will depend on what is the mass that I bring in. So we divide the force by, now I'm bringing in m2, so let's divide that by m2. So you take this expression that you have, you divide that by m2, you only have left gm1 by r squared. So it turns out that the gravitational field of m1 only depends on m1. It doesn't matter what mass you bring in. The field of m1 is basically m1's ability to let everyone else know that it is there. It doesn't care about how big a mass you bring in closer to m1. Okay, so the field is independent of any other mass that you bring in. Alright, so that is the idea of gravitational fields. The same thing can be said for m2 as well. m2 will have its own field around m1. And also note, don't take these kinds of squiggly lines to be the fields. Those are very kind of very simple diagrams of something I want to visualize for you. Okay, so the field in very plain language is the force, gravitational force that m2 experiences when it comes near to m1. So this is the field of m1, which basically tells m2 to come closer by exerting a force. All right, so now let's move on to another intrinsic property of matter, that is charge. So like mass, we have in nature another property of matter that is called charge. And while mass is only one kind, like it can be big or small, but rather mass is always positive, charge is not quite as trivial. Charge comes in two types. One is a positive charge, the other is a negative charge. And unlike any two masses that you place near one another, they will always attract. Charge, attraction, and repulsion are a little bit more subtle. If you place two positive charges closer together or two negative charges closer together, they will not like that and they will want to repel. They will want to push each other away. If you place, on the other hand, a positive charge close to a negative charge, they like that very much and they will always attract. So while masses always attract, charges are a little bit more subtle. You have to be a little bit more careful. Like charges repel, unlike charges attract. So now let's go into how we describe forces for charge, and like we did for masses. So here let's place plus q1, and here let's place plus q2. So we place two like charges close to one another, two positive charges close to one another, a distance, let's say again r between them. And as we discussed, these two charges will want to push each other away. So this is the force that 2 exerts on 1. This is the force that 1 exerts on 2. And by definition of Newton's third law again, these two forces must exactly be equal in the opposite direction. So the question now arises, is there a similar equation for electric force that it was for gravity? Well, electric force turns out is very similar to gravity, and this was discovered by Coulomb, a French physicist who did a lot of experiments in this. So Coulomb tells me the law for electrostatic force. So the force between 2 point charges, we call it F sub E for electric force, is a constant times one of the charges multiplied by another charge divided by the distance between them squared. And this K is known as Coulomb's constant, similar to how G was known as gravitational constant or Newton's constant. K can also be written in terms of another constant, which is 1 over 4 pi epsilon 0, the permittivity of free space. Okay, so look at the similarities between the two expressions. Force in both cases is proportional to 1 over r squared. So if you double the separation of the charges, the electrostatic forces go down by 4, similar to what happened in gravity. If you increase one of the charges by 2, then the force also goes up by 2. Okay, so in plain language, this is what the force is. It's proportional to the charges, inversely proportional to the square of the distance between them. Now again, you can ask, how does the positive charge, let's say Q2, know that Q1 is there? Well, again, similar to gravitational field, we can define an electric field as well around this Q1 charge, okay, which permeates, which basically transmits this information about itself that, hey, I'm here, to any other charge that wants to get nearby. So if you want to bring in a negative charge, this field tells the negative charge to come close. If you want to bring in this positive charge plus Q2, then this field tells Q2 to go away, right? So that is how we can define a field. So electric field E is the force, the electric force per Coulomb charge that you bring in. So I'm now bringing in Q2 from very far away, let's consider. Then I divide my expression for Fe by Q2. I get the field expression, which is K Q1 by R squared. So again, you see, sorry, that's not R squared. So I'm going to erase it. This is that. So this is R squared. So again, you see that the electric field is quite independent of whatever charge you bring in. It only depends on the first charge that was originally there, that is Q1. Okay, so this is how you define electric field. That is the force, the electrostatic force that Q2 will experience if you bring it near Q1. Okay, now then you would notice that electric field is defined in terms of a vector. So you may ask then, or you may simply determine that electric field is a vector, and you would be right, because force is a vector, so electric field is also a vector. So that means these kind of squiggly lines do not really work as a vector diagram, because vectors need specific direction. So if you were to draw a field for gravity, then gravity will always attract. So if you were to have a field for gravity, let's say for M1, consider this. Consider a very small mass. Let's call that M. If you place near M1, M will always know to go towards M1, regardless of where you place it. So you can place it here. M will know to go towards M1. M will know here as well to go towards M1. So the field is always telling any other mass to come close to M1. So we can say that the direction of the field for a spherical mass is always inwards radially, right? So that is gravitational field in this kind of a diagram. All right, so that is gravitational field, and gravitational field is only one kind. It's always gonna be into any specific mass that you're considering. But what about charge? Well, because charge is now two types, therefore there will be two types of field directions. It is by convention that is defined that if you have a positive point charge, then the charge will always go away from the charge. The field will always go away from the charge in a radial manner. Radial means along the radius of the sphere. Okay, so this is what you have for a positive charge, and then for a negative charge it would be quite simple to draw. You would have all the fields then going into the negative charge. Okay, so from all directions radially, the fields will always go into a negative charge and out of a positive charge. All right, so that is the electric field vector. All right, so then the interesting thing happens if you place charges close to one another. So if you place, let's say, a positive charge and a positive charge closer together, let's bring it, let's say we have, let's go back to my blue. If you place a positive charge here, a positive charge there, then Faraday gave us this knowledge of electric field lines that you can visualize how these forces, how these charges are going to be repelled. So since they're like charges, they will be repelled by electrostatic repulsion. So the fields, the closer you draw the field lines, will become kind of curved. It cannot go straight because one field is interrupting the other field. It wants to push each other away. So this field vector is now kind of curved away from the positive charge, and this also is kind of curved away because they are now getting in the way of one another. So if you draw a field like this, then you also have another field that is kind of in a similar pattern. So they will never kind of join together. So somewhere in between, you have a point in space where electric field is non-existent. It is completely zero. Everywhere else though, the electric field will be always out of the positive charge. The closer you get to another charge, the field lines get kind of distorted. All right, so this is how you draw electric field lines. Now, how does the electric field go to zero? Well, consider this. You have a positive charge, you have a positive charge. Let me get a different color. Let's say we have now this green, and I want to show you electric field vectors. So electric field for a positive charge is always out of the positive. So now let's consider a test charge. Okay, so like this small mass that I considered M, let's consider this small charge. Let's consider this charge Q and call it Q test. I can move this test charge around. I can place it here, I can place it here, I can place it here. So now let's place it somewhere. Let's take this charge. Let's say I take this charge and I bring it here. All right. And what is the electric field? What is the direction of the electric fields that I can have? All right. So then this one, let's call that Q1. Let's call this Q2. Okay. So both are positive charges. So if you place another positive test charge here, then Q2 will have a field that is quite long because it is quite close to Q2, but it is always directed away from Q2. So let's call that E2. Okay. But Q1, it is now quite, Q test is quite far away from Q1, but it will indeed also have an electric field that is away from Q1, but it's smaller because of the separation is now bigger, right? So in this region, these are two vectors that you can add up and you get a bigger vector that is also to the right. So E net, the net electric field vector, is not zero. It is in fact to the right. Both of the vectors add up. Similarly, now you take your test charge, somewhere here. Pardon my drawing. I will try and do it again. Let's say, yeah. So I bring my test charge somewhere here, right? So then what happens? Well, again, you look at the electric fields, and the electric field from this Q1 is now stronger, but it's basically outward from Q1. So this is electric field 1. And for Q2, now Q test is far away from Q2. So the electric field still is outward from Q2, but is now smaller. But again, you add the two vectors together, you get a bigger vector to the left. So the electric field is not zero. So you see, there are electric field lines in these kinds of region. It is not zero. There are electric field lines in this region. All right. But what about in the middle? So now let's take the test charge. Let's take this whole charge and let's place it somewhere in the middle. Let's say exactly in between the two charges. Well, then something interesting happens. Q1 has electric field now going to the right. It is in the middle. Same magnitude of the charges are Q1 and Q2. So then this electric field to the right due to Q1 is exactly equal to the electric field due to Q2, which is now to the left. So that means if you vectorially sum E1 and E2 in this region, the net electric field is zero. Okay, so this is quite an amazing result. All right, now I leave you with a homework. Think about what happens if you have a positive 2 charge and a negative 1 charge placed side by side. Where will the electric field, the net electric field, where will it be? Zero. Figure it out just by applying this kind of a vector addition. Thank you.